Recording in progress.
So welcome to this week's Origins Colloquium. It's a great pleasure to give the talk this week. I've been giving talks on massive star formation for many years, and most of those talks would have an image from Mark of the Orion on the front.
Not a picture of
not of you, no. But you know, as a poor theorist, I didn't really have an computer simulation, so I had this beautiful image of Orion, which now you have surpassed, and I think we're going to hear a lot about it today. But Mark has a long history in astronomy in various places, too many to name now. Let me name a few highlights. PhD from the University of Edinburgh. He has been in Arizona, in Heidelberg, in Potsdam. He was head of the department in Exeter for a while. And then in the last years has been at ESA, where he was the head of the research department and also supervising missions, also supervising all the communication about the science of those missions. He's more recently moved to MPIA, in Heidelberg, where he's an adjunct scientist. And his science interests have been, wide-ranging, but they're focused on also star formation and outflows and jets, and the dynamics of star-forming regions. Heavily involved in the development of telescopes over the years, from Hubble to James Webb, as we'll hear about. He's also very involved in communicating science, since co-founded the Space Rocks Initiative. Maybe we'll hear about this. He's recently written a book, which I heard was on some bestseller list. There's a copy here. So it's a great pleasure to welcome you, Mark, and we really look forward to your talk.
Thank you very much, Jonathan, and thank you, everybody here in the room and in Virginia and elsewhere. Thanks for the invitation to come and talk at your summer symposium, as I now know, not a school. I had to quickly change the top corner of my slide then. And indeed, Jonathan's just been through a little bit of I have a slide which shows a couple of those things, but what's not on there is this one here, being a member of the JWST Science Working Group for longer than most of you have been alive. I got involved in 1998 as one of the European proposers to join the project, because Europe is a collaboration along with Canada. And since then, I've been involved in the Science Working Group, and the observations you see today come as being an interdisciplinary scientist, of which there were 6 on JWST, and each of us got guaranteed time to then do projects. And these were defined essentially back in 2000, 2001. Some of those things have changed. You're allowed to change your science because science has changed, but the key thing I'm going to talk about in the half an hour I have more stuff we can show if you have some questions at the end, is on the Orion Nebula, which is something I've been doing since my PhD days in the mid-80s. That's the 1980s. Sorry, I just started with the old person jokes at some point. But a lot of collaborators working in various parts of this, the jets and the outflows on the Orion Nebula. You can see the names, and you'll see that in the recording later on. I think we'll have at least one collaborator online, which is Nick Ballerin, and I'll show a little bit of the stuff that we've done together right there as well. So let's see. It's going to take a while for these things. So that's just a rundown. This is the sort of classical being an astronomer moving around the world thing. And I know astronomers who've done many more flags than that. But the MPIA, where I am now as an adjunct scientist, having retired from ESA last year, I should point out ESA retires people very young and pushes you out the door. It's kind of French civil service thing. So I think I've still got some science to contribute, which is why I came back to MPIA. But I was there in the mid-90s. And that's the reason that we decided to go back there. So I have an adjunct position there. Now, some of the science we've already heard, and much of the science that you tend to hear these days in astronomy is in some ways quite different to when I started in astronomy. And it's huge samples of many objects, which then need all sorts of different techniques to sort through the statistical samples and pull out interesting facts. So there's here, in this case, I'm sort of illustrating this with a swarm of locusts. You're not necessarily particularly interested in individual locusts. You're interested in what they do all together. So you might have huge samples of galaxies or of molecular clouds or of young stars. Looking at the statistical properties is very important. But I'm kind of an old school astronomer in some way, and so I'm also very interested in focusing in on individual things This is not a locust, by the way, but it's a dragonfly. And this was partly my pandemic sanity hobby in my back garden, macro photography of insects, including the many dragonflies we had in the Netherlands. So that's as a preamble. My background is in instrumentation very early on in building infrared cameras, the very first cameras with more than 1 pixel. Imagine, even in my lifetime, infrared arrays didn't exist, and you had to make maps by scanning across the sky. So the results you see before the mid 80s were all taken with a single pixel scanning around like an old TV. And because infrared detectors are really good seeing through dust, I mean, they're useful for many things, of course, in the infrared, such as high redshift galaxies. But my interest was in star formation. And one of the things that we did very early on was go to the Orion Nebula, because that's sort of a mandate in astronomy that every new instrument has to be tested on the Orion Nebula in some form or other. So I don't really need to tell you where it is. There's the constellation of Orion, and down at the sword, of course, and my cursor should show up there. The sword is where the Orion Nebula is. So some very bright OB stars up to tens of solar masses, ionizing and ablating this big nebula, the Orion Nebula. And the very inner region of that is seen in this image from later on, so now 2005. This is the central part of the Orion Treasury project led by Massimo Roberto. So this is multicolor imaging at visible wavelengths and is dominated here by emission lines. So hydrogen alpha, oxygen 3, sulfur, and so on. So in that region, you can see right in the very center, the Trapezium stars, the group of 4 stars in the middle. You just about see it. It's kind of burned out on the screen. It's perfectly fine on the laptop, but it's just the nature of Zoom. But what was discovered by George Herbig and in fact Trumpler in the 1930s is a cluster of faint red objects, which you see if you get rid of the emission lines, you can see right into the core. And that thing was called the Trapezium cluster. So many people call it now the ONC, the Orion Nebula cluster. It's a rather larger structure that extends over much of this region here. The Trapezium cluster is what's in the very center. And over the years, through ground-based work, but also with Hubble in the early days, even when it had spherical aberration still, it was possible to start assessing those stars, and through imaging and spectroscopy, learning that these are typically 1 million years old. They span the IMF from, say, 50 solar masses all the way down into the brown dwarf regime. But the real way you want to do that is by looking in the infrared. Because the infrared penetrates the gas and dust which is in those regions. It also looks at low mass, cool objects, because most of their radiation is coming out at longer wavelengths. Just as an aside, one of the things that you may have seen down the years, and we'll see some more modern versions, something I did with Bob Odell and John Bally in the mid-90s, we've discovered these images right in the very center of the Trapezium cluster in the Orion Nebula, where we see circumstellar disks as silhouettes against the background nebula. So you see the small red dots in the center, those are the low mass stars, and they're surrounded by these silhouettes of gas and dust. Just again, to put things in a historical perspective, when that image was first made by looking around the region and making that montage, I showed that at a conference in, I think, 1995, and the speaker after me, his talk was titled, "Why Circumstellar Disks Don't Exist." Because it was controversial at that point. I mean, it seems entirely obvious that they must and that they do and that planets must form in disks. But it was still reasonable in 1995 to say we have no real direct evidence for them. The speaker hadn't seen my talk when he wrote his, so everybody just said, look. So this is now taken as of course, obvious, but over my career, that has changed enormously. So let's zoom into the center, the inner part of the Orion Nebula. And now, maybe a little more clearly, just again with the contrast on the screen here, you can see the trapezium in the center. You can see the thing called the bright bar, which is this diagonal feature, and then more OB stars down to the bottom left there. But because this is an optical image, you don't see the rest of the young stars very well. So in 1986, for my PhD thesis, we took the very first camera on the United Kingdom Infrared Telescope in Hawaii. This had 4,000 pixels. But it's 4,000 more than the one we had the week before. So it's a big increase. And we were able to then mosaic around and make a map of that inner region. And so this is the map that appeared, or the image that appeared in my PhD thesis. And I was very proud of it at the time. I'm kind of embarrassed showing it now, but that just again tells you how technology has moved in my lifetime and will move during your careers as well. So everything you do today, if you're still in astronomy in 30 years' time, you'll look back and be quite embarrassed by it. But that's a good thing. That's how we progress in science. Now, a little bit later, a year later, in fact, we went back and then could take our first color image using 3 wavelengths in the near infrared. And now you can see the trapezium clusters, very dense association of up to 50,000 stars per cubic parsec. So if you put our sun in this image, it would be in the bottom corner, and Alpha Cen would be in the top right corner. So that parsec scale, in that volume, there are thousands of stars in the Orion Nebula. And we think the sun formed in a region like this. There are reasons to do with the tilt of the ecliptic relative to the solar rotation axis and so on that give us the idea we might have formed in a very dense cluster like this. The only image Jonathan was talking about came about 10 years later from the VLT. Larger field of view, larger detectors, better seeing, much better seeing on Paranal in those days. So this is sub-arc second imaging and is sensitive when you look at the very lowest mass objects, the faintest objects. The lowest mass objects are around 3 to 5 Jupiter masses from the photometry. This is not proven dynamically, but by looking at models of 1 million years old and looking at the photometry, you can say these are a few Jupiter masses. And one of the big questions which motivated my guaranteed time observations was, where does it actually end? How far does it go? Does it go below 3 or 5 Jupiter masses? Theoretical predictions would suggest that clouds can't fragment. They can't cool down quickly enough to then fragment to smaller masses. So does the IMF just terminate it? Does it end? Or could we, with JWST, or as it was then called NGST, the Next Generation Space Telescope, could we see much fainter objects in the Orion Nebula? And so that then, by fast forwarding to 2022, led to the new data that we got in 12 filters, so not just 3, so the short wavelengths and the long wavelengths. And I don't know, the resolution of this screen is HD, I guess, 1080 or so, but the underlying image is 21,000 pixels wide. So there's sort of no way of getting into the full view at detail. I've done the calculation. The largest screen in the world is the Sphere in Las Vegas. It's enormous. It doesn't have enough pixels to show this image, 1 pixel per pixel. So we should rent it, though, nevertheless. So this is the short wavelength image, and typically what you see with JWST press release images, you'll know that JWST takes short wavelengths and long wavelengths simultaneously. So if you decide you want to study at 1.5 microns, you will get a chosen wavelength, long wavelengths as well. And usually they're blended together to make one color image with a kind of JWST look. I vehemently oppose doing that because the resolution of the telescope is wavelength dependent. And if you want to see the smaller scale structures, my dragonflies, you want to keep the short wavelength stuff separate from the long wavelengths. Otherwise, it all just gets blurred out at the long wavelengths. So this is a short wavelength composite from basically 1 micron to 2.1 microns. And we do have an equivalent long wavelength mosaic. This is mostly ionized gas. And in this case, now in the long wavelength channel, the green stuff is PAH emission at 3.3 microns. So we see much more of the destruction, if you like, or the evolution of the H2 region as a blister on the front of a giant molecular cloud with the trapezium stars in the middle. And what you see also, when we come back to this a little bit later, is the very bright BN object, the red thing further up to the top right. That is a massive, probably protostar, something that's been forming in a region in a molecular cloud behind the Orion Nebula. Exactly where it came from, though, is still a debate. And so I'll come back to that just a little bit later on. So let's go back for the time being to the short wavelength image. And then, as I said, most of this is ionized gas. And if we now isolate one of the filters, and this would be Passion Alpha, 1.87 microns, which you can't see from the ground. It's in an opaque region of the atmosphere. So this is the first high definition, if you like, image of the Orion Nebula in that wavelength. So we're just going to zoom in on the middle. Of course, we have it for the whole thing. But if we now just look in this small section, the middle here, and zoom in, Now the stars, because the filter is very narrow, the stars get fainter. You don't get so much continuum light, but you get a huge amount then of the ionized gas. This is essentially arising in the same way that H alpha does in the visible. So the thing you then think, well, let's compare the JWST data in Passion alpha with the HST data in H alpha. They have roughly the same spatial resolution. JWST is bigger, so it should have higher resolution, but it's at longer wavelengths. So the resolution is equivalent. So if I now make a little movie and show you the comparison, we'll see how it plays on Zoom as a movie. It's not really great at doing these kinds of things. Now, the key thing you'll see is that things are moving because, of course, there's a 17-year time baseline between these images. So we're not just comparing gas at certain locations. We can see stuff moving across. So if I just draw your attention, there's a weird kind of cavity moving here very rapidly. And I've put in a scale bar, 100 kilometers per second. That's the length of that little bar over those 17 and a half years. But then there are jets and outflows, which are moving. I guess, yeah, if I move my cursor around, you can see the jets and outflows moving fairly dynamically at maybe 50 to 60 kilometers a second. And if you look very closely, you can see some of the ionization fronts in front of these so-called proplids. These are the externally irradiated disks, which have circumstellar disks with dust and gas, and they're being photoionized by the OB stars in the center. And that material is then streaming away, mostly in tails pointing away from theta 1c. And this is what Jonathan alluded to, and Orion is online at Ryan Boyden, and they have a bunch of time to be looking at these with the mid-infrared spectrograph on JWST, and they've been doing ALMA work. So this is a complement at the near-infrared to the work that's been done with Hubble and then the longer wavelengths. But you can immediately, if you look very carefully, you can actually see the ionization fronts, the standoff shocks, are moving outwards slightly over 17 years. So there's evolution in the proplids over that time scale, which you would expect, but you can now visually see it. So there's a lot to be done by comparing the HST data and the JWST data. But let's just go back now to the short wavelength image. And those ionized proplids are things which are close enough to the trapezium stars that the UV flux is high enough that the dust and gas is being ablated and removed. But there are disks in the region which are further away, either in the line of sight or further tangentially. And I showed the examples that we had from Hubble back in the 90s. And this is where I just want to advertise this particular object. It's one that's so big that it can be seen from the ground. It's almost 2 arc seconds in size. So in this case, the disk is edge-on, and you don't see the central star, but you can see reflection nebulae above and below the plane of the disk. So there's a central object in the middle there, and then you see the disk. And you can see some structure in the disk. It's not completely asymmetric, but the work that Nick led and I was part of as well has analyzed these data because although it looks in this image opaque, it's not. You can actually see through the disk at that wave in the infrared. And by looking at different wavelengths, you can then make effectively a transmission spectrum of the background light coming through. And that was a paper that we published. It was published at the beginning of this year. And what we find there is that in the ansae, so the dark ears, if you like, of the disk, so the darker stuff in that top picture, you can see that there's ice absorption in the spectrum. So we can see directly that there's ice on the dust grains in that disk. This is not new in and of itself. We know there's ice in circumstellar disks, but this is a new way of showing it. Problem will be extending that to others because most of the disks are a lot smaller than that. And also in the near infrared, many of the stars are much brighter. So we don't get as good a comprehensive view of the circumstellar disks. But here's just a little sample of some of the ones we do see. So the same one in the bottom right corner there. We see disks, which are, again, several cases where they're edge-on, some where they're ionized in the bottom left here, with this big teardrop shape around it, some with no ionization at all, but completely edge-on in the middle on the bottom row, and then some of the smaller objects on the top left and the top right, where you can see very clearly the flared disk, or the flaring is probably an artifact of the point spread function of the telescope. It's probably likely to be flat in reality, but then you bleed in the reflection nebulae and that makes it appear flared. And we see a little bubble of molecular hydrogen wrapped around the outside. And some of this work has been done by the ERS team, PDRs for all, and more of this work is being done by other people now. But there's a huge sample of these objects to be followed up. And we see different things with the JWST data than we see with the Hubble data. They're actually higher resolution to begin with, but also we see PAH emission, we see molecular hydrogen, things that the HST data didn't see. So there's a lot to be done on the proplyds and the silhouette disks as we move on. So now again, going back, one of the big questions I said before is what is the lowest mass object that we can find in the Orion Nebula that formed, if you like a star? And what we're going to do now is just zoom into this very small region here, and now come in at full resolution so we get a much better view. This is again the near infrared, and your eye, hopefully on the screen you can see it, might be drawn by the fact that across the top half of the image, there are 5 pairs of more or less equal brightness objects, a separation typically of a couple of hundred AU. So they're not closed binaries at all. And if you do a statistical analysis of the field, you can see most of it's empty. There's just not lots of objects in this region. At that brightness, if they're in Orion and they're around 3 to 5 Jupiter masses. So firstly, we're finding objects we kind of knew were there already, but in pairs, and that's totally unexpected. There's no extrapolation from the brown dwarf binary frequency, which should be declining. You'll see in a plot in a moment. These things really shouldn't exist. So there's I won't describe it, but this double peak here with a very sharp peak at the small separations is the way we've characterized the clustering fraction. And that says it's not just chance alignment of various objects in the region at all. As I said, we can fit the spectral energy distribution and see in the JWST imaging, we can see tentative evidence for absorption features due to water and even maybe due to methane at the longer wavelengths. And that's the way we characterized these objects as being in Orion rather than field objects. And if you do statistics on these objects, originally we call these things jumbos, partly to get sponsorship from a big Dutch supermarket. So it's a joke. But Jupiter mass binary objects. We originally thought we had around 40 or so, but we did a much more rigorous pass through with some referee comments, and it's come down to about 20 or 22 of them. But if you take those numbers and you do statistics, you see indeed the binary frequency of brown dwarfs, so higher masses to the right there, lower masses to the left. The binary frequency function drops almost to 0, and then we think if these are all what we think they are, it would rise again. So that's completely unexpected. But what you can do if you only have the photometry is you can go in and assign some masses to them. And those masses in those objects, again, purely on the photometry, the candidate masses would be a few Jupiter masses. You can see the numbers 3, 4, 5. And these pairs at a typical separation, typical brightness. Very suspicious, right? Again, if this was chance alignment, you wouldn't be seeing things at the same brightness like that. So these are physical pairs, but the question is, what are they? So the way you want to look at that, of course, is spectroscopy. In cycle 2, we did follow-up spectroscopy. Some of this data is public, and some other people have published some of this already. We have more that will be publishing soon, which is still under proprietary restriction for a little bit longer. So this is multi-spectroscopy with JWST. Each one of the slits there, in some cases, contains an object which we're trying to get spectra of. And those spectra, these are only at low resolution, so resolution of 100 or so, but you can see water absorption in the near infrared, and you can see shapes in the longer wavelength, some methane absorption, but very, very little of that, less than we thought. We think that that's due to a combination of effects in the spectra, because we're not actually fitting the models particularly well. So we don't actually know that the pre-main sequence models at these very low masses are right. But there's also a degeneracy in there, which is a concern. So if we compare our one model spectrum to a range of spectra at, so L0 down to L7, so this is hotter and this is colder. But if you then vary the reddening at the same time in the other direction to keep the object the right brightness, they all fit very well. So at this resolution, there's a factor of 2 or 3 in uncertainty in the mass at least. And in fact, if it gets a little bit worse, if you look at different models and different standard spectra, we see a range of maybe a factor of 3 in mass. Now, this is all assuming that they are still in Orion and 1 billion years old, and we have now characterized a bunch of them as just being field stars. So we do know that not of these jumbos, some of them are field stars, but we've got spectra for one, but not for the other because it's too faint or it's in the wrong place in the slit. So it's a pretty messy picture at the moment. So I'll take questions on that later on, but there's a lot to be said, I think, about that. Now, an area that I know Jonathan's interested in, we've been discussing, is this BN region up here with these enormous fingers of molecular hydrogen emission, which are spraying out from some point down here towards the bottom middle of the image. And the idea here, the belief is this is a fragmenting shell of material that's been expelled from some kind of explosion event. And as it's expanded out, it's fragmented into these fingers. So it's not like a jet or an outflow where there's just a bipolar, one jet going one the other way. This is some kind of bubble blowing apart. And you see that most clearly in the ALMA data that John Bally has, because then it doesn't suffer the extinction that is prevalent towards the bottom of the image. But if we now zoom in with JWST towards the top of the flow, we can do the same trick again. We can go back and look at archival data, so adaptive optics data taken more than 10 years ago in molecular hydrogen, which is the red emission here. The green emission in here is iron 2, so this is atomic gas. And at the very tips of these things, there's white material, and that's ionized gas. So the energetics, there's most of the energies at the front of the flow, but then you get these wakes behind. So if we look at the old adaptive optics data in comparison, you see things very clearly expanding outwards from the center at the bottom of the image, but also the bow shocks or these wakes are expanding sideways. So we can characterize how this shell fragmentation is changing over time. And you can see, well, there's a lot to see in these data when we have a look at them in more detail. But I'm conscious of time, so let's...
well, maybe 5 minutes, it's okay.
Yeah. And just to put it in scale, there's 250 kilometers a second at the top there. So these things are moving pretty fast. If we go down in the flow, we see something very similar. Now we have BN has come into the picture down here. We can see the flow expanding in all different ways. And because of a projection effect, the things closer into the center of the flow, they're coming towards us. So they don't expand tangentially so fast. Much of it's coming towards us. And then we go down to the very bottom. And we can see some material to the bottom left here expanding outwards across the top of the trapezium as well, confirming that this is a fairly, a flow which expands over nearly 360 degrees. Now, if you can see very carefully, it's been registered on the stars. The resolution difference makes it a little difficult to get a hold of, but you can see one object moving quite rapidly, a point source in there. And it's this thing here, and it's called Source X. Now, Source X was discovered a number of years ago with HST data, and you can measure its proper motion, and you can find that proper motion is around 60 kilometers a second moving across the sky. And the real question is, where did it come from? What actually happened? And so I put an arrow now above it for the Becklin-Neugebauer object. The current theory, which Jonathan doesn't believe, which is fine, we're going to work on it, is that both BN and Source X came from a common center around 500 years ago, and they're both expanding away from that. So this is now the long wavelength view of this region in this box. And Source X is labeled there, BN is labeled. But in fact, if you look at radio data of the compact sources in this region, the radio VLA and VLBA data have much higher spatial resolution for compact sources. So they can go in and actually see the proper motions in great detail. They've been looking for almost 40 years. And there are a whole bunch of objects in there in this overlay, which are all expanding away from a common center, again, around 500 years ago. The exception of the object at the top there called IRC 23, which is maybe 300 years ago. So was there just one explosion? Was there more? But the real question is, how did that happen? How do you dynamically eject something at almost 10 solar masses, BN, if you don't have other objects at the same masses which have recoil? So I think Jonathan's right to be curious about this, because if you do trace BN back, it could have come from the trapezium thousands of years ago, rather than 500 years ago. So is it just passing through the region and all the others are expanding away from that source? Because BN is the most massive. So we're looking at the moment, we'll be spending time this week looking at the proper motions from JWST and archival data. Problem is BN is so bright, it's really hard to see and measure its position accurately. So I want to show you two more things, curiosities. One of them is coming back to the fingers at the very top. I said that you see ionized gas, followed by atomic gas, followed by molecular gas. But it actually is weirder than that, because if you look at the very tips of the outflowing materials, all this stuff is moving up. You actually see red emission in spikes ahead of the ionized gas. So that's molecular hydrogen. So the question is, how is the molecular hydrogen being shocked or fluoresced in a spike along the axis of outflow? Is that through magnetic fields, perhaps? There are discussions about maybe it's not jump shocks, but continuous shocks, channeling some energy out in front through the magnetic fields. There's other thoughts that it might be due to cosmic rays, which are enhanced in outflows, and magnetic fields play a role there. It turns out that if you look at the data from Hawk Plus, so SOFIA data, you can't quite see it here, but this is a map over my old image of the magnetic field, and it does actually extend in the right direction out in the flow. So the last thing I want to talk about is something deeply weird, and that is that when we look in one of our images, the shortest wavelength image we have, which is F115W, so around 1.1 micron, we see things that don't make any sense at all initially. And that is, in that filter, and only in that filter, we see dark shadows appearing around stars, around proplyds. So I call them coffee stains, and you can see why. They've got these weird shapes. There are places in the region where there are very compact absorption features. This little dark spot here is not a silhouette disk because it only appears in this wavelength, in this filter. And in fact, if you zoom in, there's an object in that same field, which is completely bananas. This one I call the stupa because it's got little bubbles coming out from the top and flat parts going out the other way. So it looks like a stupa temple. Exactly. So something's flowing away from that star, but what is it? What's the material? What's causing the absorption? And to prove that it's not in any other wavelength, so this is one of these features, of which there are many, this kind of weird arc-shaped feature with some tendrils around it. There are some little dark clouds there. They're only seen in this filter. They're not seen in any others. And so to prove that, I'll show you a movie going from the Hubble data at shorter wavelengths through then to the JWST data. And only in one of the filters will you see these features. That one, F115W. And then they go away again at the longer wavelengths. And you go cycle back to the HST data. It's not in any of the HST filters. Suddenly it's in that filter. And so the question is, what is it? Why do we see that? And the answer is, we know, is that it's helium-1. So that's helium-1 emits at 1.083 microns, 1083 nanometers. So this is one of our spectra now of the Orion Nebula. And if we zoom in on that, the F115W filter sits in this region. This is 0.6 microns to 1.5 microns. And that 115W filter sits right on top of helium-1 and a little bit of Passion beta. But we don't think Passion beta is playing a role because if we look in the J band, the ground-based J band, that is a somewhat longer wavelength, and we don't see this feature in that, even though it includes Passion beta, but it doesn't include helium-1. So this is helium-1, and the way that that happens, we think, is that you have to get this gas into an excited state, into the metastable triplet state, and it sits in that state for many hours, and background photons coming from the PDR in the helium line, there's lots of helium in Orion, come through and de-excite that line, so they get absorbed effectively. And then they, because they've pumped the line, they then radiate out isotropically. So while it's coming towards you along like a laser, then it gets re-radiated isotropically. So that means a net drop in the intensity. And we've been doing work on looking at this at high spectral resolution now with PriRes on the VLT. And we're looking at how the triplet line changes, how the different components of the triplet line change as we move across. And so this is work with Tom Howard at the University of London. So the very last thing is that although I showed you a case where these are bubbles around young stars, the most peculiar case for us so far is if you look here, this is now not F155W, but it's F140, so 1.4 microns. There's a classical proplid with an ionized bow shock around the outside and a jet here. You see the ionized gas there. But if we now switch back to the 115, you see it appears in absorption. The outflow appears in absorption, which you've never seen before. And outflows don't appear in absorption, they appear in emission. So the gas in the outflow there's helium there, and it's absorbing the gas from the background. So it's not a silhouette disk, but a silhouette jet, if you like, in the same way. And there are more examples of that. I'm conscious that I'm going to finish just in a second. So there's another one up here where we see the same phenomenon. There are a bunch of jets in the same region where we see the same phenomenon. Jet seen in absorption. The really interesting thing about that is it might give us access to the bulk material flowing out, and maybe we can measure the mass of the material in the jet that way, better than just looking at the excited material. And if you take the 115W image and divide it by 140M, thanks, Al, and zoom in. So now you've basically subtracted the continuum, or you smoothed out the region. You can see all the little black patches around here, around the stars, these coffee stains and so on. So there's a nice way of being able to do a big survey, and that's what we're doing right now. And one of the lovely ones you see in this image, down by the bar here. So the jet I pointed out before is over here on the image in absorption. But look at this feature all the way along there. Huge, long feature, only seen in absorption, not seen in emission. And we know that that's real because if you look with HST, there's a propellet down at the bottom of that thing, and there's a little microjet coming out for it. So we know that that's a jet which is winding its way parallel to the bright bar there, which is pretty cool. So that's the end. I just wanted to remind you that you all look young and beautiful today, but you will get older because, the clock of time only proceeds in one direction. So make the most of your summer symposium and being young. That was when I finished that's my PhD thesis when it was still a big bound book. That's me with JWST a month before launch. But because I'm in Heidelberg, I get to now play with other big things. I was on the science working group for the ELT for many years as well. And now that's coming to fruition, even higher spatial resolution for spectroscopy and for imaging. So there's a lot left to go, I think, but I'm happy to collaborate with younger people who have more time and energy than I do. Thank you.
Thank you very much. So that was a great overview of Orion, and we have time for questions and discussions. So usual process, just raise your hands. Zoom as well. Maybe Ryan in Virginia can help me there.
Yeah. I mean, I should say, as you're gathering some questions, there are a bunch of other things which we've looked at with JWST, outflows and jets. So if people want to know about some of those, there's slides there for that, and some outreach stuff as well. If we have
exactly right. So perhaps we can organize a little bit. So obviously you focused on Orion,
yeah.
But as we know, you've used some of your James Webb time in other star-forming regions. Perhaps let me ask first, and is there something you'd like to highlight from another region, just to give some perspective?
Yeah,
oh, beautiful, but quite strange.
Yeah. Well, I mean, we've been looking at isolated jets and outflows as well. And one of the sort of classics we've been looking at is a thing we discovered in the 90s called HH211. So this is IC348. And we actually looked at the wrong place. We were looking with an infrared camera. We were supposed to go and look at IC348, but we looked in a paper catalog because there was no online in those days. And we got the wrong coordinate. It's an object called IC348 infrared IR, which is down here. And the reason we got to that first is that it appears first in RA order. That's how things were in those days. But luckily enough, we found something very interesting in there, and that's this jet, which was the first ever protostellar jet seen coming from a class 0 protostar, so very, very young. And it's seen here in molecular hydrogen. This is a late down the middle there, and there's probably a binary protostar in the middle. So it's actually, as the binary orbits around, you're seeing changes in the orientation. And you see entrained bow shocks of material pushing out into the cloud. So we have a bunch of data there, which we published. It was front cover in Nature, which was nice. Also spectroscopy, both in the near infrared and the mid infrared. Including MIRI mid-infrared IFU imaging, so actually studying this whole end of the bow shock in all of those species there. But what I just wanted to show in a second briefly, so there's a lot of, there's a huge amount of chemistry, astrochemistry you can do here, and that allows you to construct your model of the various layers of molecular and atomic gas. It's mostly molecular, this outflow. And then if you go into the center, the protostar is invisible, of course, at near-infrared wavelengths, but it's been studied heavily with ALMA over the years. So now you can see the inner protostar. It has a circumstellar disk. It's more or less edge-on. But the thing we've been doing with JWST, and I'll stop up just after this part, is measuring proper motions. And we've been doing that by comparing the old VLT data with the JWST data firstly. So over a 20-year period, you can see substantial motions. And those are typically 50 to 100 and 150 kilometers a second. But we're interested in doing it at much higher spatial resolution. So I'll just show one example before stopping. This is now comparing 2 epochs of JWST on the southern flow here. So if I put that movie, so this is over 800 days or so. And you can see actual quite differential motion in the flow between different parts moving, some parts not moving at all, or certainly much more slowly. So we have a lot of access now to information about the detailed change in the flow, the velocity. We have that for several flows now. So, but I'll stop there for the time being.
Great. Marina, please.
Yeah, I have a question about jumbos. There
Yes.
was a paper just another day by Kevin Luhman,
Yeah.
who said that based on the spectra, all of these jumbos have a color consistent with background objects, and only isolated objects appear to have color consistent with brown dwarfs. I was wondering if you have seen that paper, or if you have any thoughts on it.
Yeah, so the original list of jumbos, which is the list which is public at the moment, has the 40-odd objects in. So we already know that half of those don't really exist, or at least they're not consistent with 1 million-year-old low-mass objects. And we know that from our reworking of the photometry. So it's a bit unfortunate that our paper was rejected by Nature on this for reasons which I will discuss over a beer with somebody, but I won't certainly put it online on record. So we've been reworking the photometry, and we know that half of them aren't real anyway. And that's the problem. Kevin has taken our spectroscopy of some objects, which we knew were likely to be background anyway. So I don't think that necessarily kills them. What we've been finding, though, is slightly problematic, which is that because of the way the spectroscopy works with JWST, you can only have fixed slits at a certain pitch across the detector. You can't place them completely arbitrarily. And in most cases, you've been able to get a spectrum for one of the objects and proven that it is low mass or not, but not for the other one because of the orientation of JWST. So it's a really mixed picture at the moment. Right. We do have some which are 10 to 13 Jupiter masses, so just around planetary, which we do confirm both of them as being in Orion. So we don't agree with Kevin on this, but that's because he's operating on an incomplete data set. The rest of our data are not public yet.
Let's try and synthesize the jumbo story then. The pairing, it looks very convincing in terms of they're not just random alignment.
Yeah, well, that will be the outstanding question. Imagine we prove that these are all background objects, M dwarfs, let's say, and some of them are, some of the components are. How do we reconcile that with them being these roughly equal brightness binary objects, and several of them in one location?
Right.
Because we don't see that elsewhere. We don't see it in other regions we've looked at with JWST. So I'm not saying that we say that they are 1 million years old in Orion. I think that we just don't quite know as convincingly as Kevin has tried to make
Well,
it.
I've always said that there should be age spreads of up to, who knows, 5, 6 million years
Yeah.
in Orion. What if they are 6 million years old?
Well, they should be more dispersed then. And so the fact we find 5 or 6 of them in one very small region is a bit suspicious as well. One of the things that people have said, their background AGNs, well, firstly, finding that number of equal brightness AGNs isn't going to work. And we know they're not extended at all, these objects. We've been very careful about that. So I don't know the answer to your question really, Marina, but I do know that Kevin has sort of been on a bit of a crusade, let's put it that way.
In any infrared excess from those sources?
Yes, yeah, we fit. So what we're doing now, we fit the spectra, the photometry with infrared excess, and we fit the spectra with infrared excess. So we do see it, but that doesn't tend to affect the spectral ID of the object, which is mostly based on the short wavelengths. So we see it rising. So we do see very low mass objects with DIP.
Any recombination lines?
Not at this resolution and sensitivity, no. I mean, and the other problem is that in the observing time we had, because it was limited by what I had from my program, there are many objects which are just too faint, so they're ambiguous at that level. I mean, these are objects close to 30th magnitude, or not too far away from that.
Okay, we may come back to them, but let's take more questions. I see Ruben is next, I think.
Yeah. Hello, Mark. Hello, everybody. Thank you very much for the nice talk. It was awesome. Very nice to meet you. I couldn't be there for my newborn, actually. But anyways, I had like a few questions about jumbos, but I think many of them have been answered. And let's focus on the jet, which is my sweet research here. I was actually a few months ago with John Bally, actually, in his conference, and we were discussing exactly those tips of H2, kind of like ahead of the ionized material. And we were wondering actually if those, say, bullets that are emitting in H alpha or any reclamation lines are actually emitting UV photons to ionize the H2, you know, the way like to pump.
Yeah.
But do you have any thoughts on that? Because, you know, that's...
Yeah, we do. So obviously I've talked to John about this. We're collaborating with John on some of the work. The problem with that, so the idea is that you have a lot of hot gas at the tip of these, if they're physical bullets or fragment the part of the shell that's fragmented and is higher density. We know that they can get very energetic because at least one of those has X-ray emission from it, from the COOP survey that Eric Feigelson and others did. So we know there's plenty of photons, high energy photons kicking around. But we do see actual extended molecular hydrogen in a kind of wrap around the end, but that wouldn't explain a spike going out in a straight line. I didn't have time to show it, but what's weird is we see those spikes on some others of those fingers, and they're not always in the direction of outflow. They're sometimes up to 20 degrees off the outflow direction, which is possibly linked to the magnetic field argument at that point, because the magnetic field is large scale threaded through there.
But do they all have spikes?
No, not all of them, because some of them have kind of broken out and you're only seeing hotter gas moving away. I mean, remember, we typically only see these things in the infrared. Some of them poke into the H2 region, one's coming towards us, and we see them in ionized gas in the visible as well. But the tips of these things, some show spikes and some don't, is the way.
I mean, the bullets in general are strange. Perhaps you can say a little more on what the current thinking is of how you can have these features. I know John Bally has been looking for other examples in the galaxy. There are a handful of...
Yeah, well, you know...
Nothing quite like...
Well, as I think maybe you said or other people have said, isn't it bizarre that the only real definitive example we've seen of this just happens to be in the nearest star-forming region and just happens to be from an event that happened 500 years ago? We don't like this in astronomy, right? We don't like these coincidences. But it's true that there is really nothing similar on this scale. But the model that I kind of hold to, because we wrote a paper about it many years ago with Mordecai and Mark McLowe, based on a model by Jim Stone, is that there's a big shell that gets, swept up. And just through the hydrodynamics, it fragments into these bullets. So Jim shown through supercomputer simulations years ago, maybe it's changed now, that you will fragment this shell as it becomes unstable as you expand outwards. So we don't, in my mind, they're not physical bullets, like something fired from a gun from the original source. There's just way too many of them, and they're sprayed over all sorts of angles. So I know John's picture is this kind of expanding, fragmenting shell as well.
We'll come back to Ruben at this time, but I think we should take the next question from Orion. We'll come back to Ruben.
Hi, thanks for the presentation. It's great to meet you over Zoom, Mark. I wanted to ask
finally,
about
I've been following your work for a long time, but
thank
so
you.
here we
Me
are.
as
And
well.
this-
I remember reading your
10
first
pixels on
papers
the
about
screen.
proplyds and being amazed by the silhouette disks and everything.
Yeah.
I wanted to ask about the proper motions of the proplyd ionization fronts. Have you been able to measure those from comparing with the HST images about maybe both the heads and the tails? And if so, what are those expansion velocities, and are they consistent with the 10 to 20 kilometer per second values for photoevaporative flow?
Yeah, I think so. I mean, so I haven't done a comprehensive study, and as I told Jonathan earlier on today, much of that work is what I call keynote astronomy. I think Alyssa Goodman has the same, where you align things as best as you can before you then start getting into the numbers. So if you think of a classical proplyd as a tadpole with a head wrapped around the disk and a tail, I don't think I see much evidence for too much motion of the head of the tadpole moving forward or the tail moving backwards. What I can easily see is the wraparound bow shock around the front, the standoff shock. That's definitely moving forward at maybe 10 to 20 kilometers a second. But what we can do, and it's on the long list of projects, is that we can go in, and Nick knows this, we can go back to the JWST data and actually make higher resolution versions or by doing the drizzling better a second time, because we were optimized for these huge mosaics. We weren't optimized for individual objects. So I think that would be the thing to do, is go back to the data. We know a lot about the problems of the data. I mean, JWST images look amazing, but if you've ever worked with raw JWST data, not quite. There's a lot of work in putting those things together. So I'd be very happy to talk to you about that, because I know you have this big MRS program and you've been doing the ALMA stuff. So maybe we can use this pixelized view to start talking to each other and exchange some emails. I'd like to do that.
I don't know if anyone's really directly measured the expansion velocities of the fronts over large samples. I think it'd be an interesting constraint for the photoevaporation model.
Yeah, you probably know I work with Tom Howarth at Queen Mary, and this is something he's very interested in. He's in your collaborations as well. So I think these things all line up, and we should have a talk about that. Yeah, because you're right. I mean, you look at the data and you see it, it's there, but then quantifying it and making it statistical, turning it into a swarm of locusts, as I say.
Orion has the radial velocities, of course.
Yeah, and that would be the important thing too, because these things are all in projection. And so you might see some spread. I know Tom has a student who, shocking, her name evades me right at the moment. I met her a few weeks ago, is beginning to look at exactly this stuff. So I think it's important that we tie that up.
Okay.
Yeah, definitely.
Great. Leon, please ask your question.
So in other contexts of astrophysical shocks, when the contact discontinuity breaks through into a region where there's different gas, there tends to be either a scalloping effect, you break through a bubble, or there's basically a point where you're able to break the front of the shock. And so with these fingers, is there a chance that that's what's happening, that you're going into a region where either the gas is ionized, there's a different molecular composition, there's more mixing in front of it, or something like that?
As I understand the model, it's interacting with itself in the sense that there's a shell being swept up at a higher density than what's outside. So it doesn't really matter what's outside. It's the shell itself which is fragmenting, as I understand it. But almost all of the stuff you see that's in red there is occurring in a molecular cloud, OMC1 behind. Occasionally, some of them are pointing towards you and you see them ionized by the OB stars. So some of them are breaking through into a much lower density region and a hotter region. So whether there's an actual difference in the structure of fingers which are confined to the molecular cloud and others which might be coming out of the molecular cloud, that's a good point. Maybe now we have enough proper motion data and structural data, maybe we can see it. But
we're talking about shock physics then. Do you have the resolution to resolve there are shock zones, right? How thick they are, and I know the collisionless shocks they've been resolved in the past, right? Even with HST, isn't it? Here,
it's hard. It's 400 parsecs nearly, and the higher the resolution, the more these shocks seem clumpy. So whether we can go and find examples of the very sharp edge. I mean, of course, we see lots of extended fluffy emission in the wakes, which is clearly highly resolved. But the front of the thing.
You have a data set now because you have the proper motions of the of course of the.
Well, we have them in Keynote Science version, but yeah, we tell it into numbers soon.
But soon, real numbers of proper motion, so you know how fast this thing is propagating through the ambient gas, and there's surely ways to do experiments on
yeah, I mean,
shock physics.
To some extent that's not new because people have been studying this for a very long time, and so John has proper motions and so on. These are typically restricted to the peaks of the outflows, just the way you centroid the tip. So as we were discussing earlier today, I'm actually very keen, anybody that has a good understanding of I don't want to call it machine learning, but image processing as used in machine learning environments or as used in the people I'm talking to or in the video effects industry for filmmaking, how you might be able to make a 2D image of the velocities, not just by looking at individual points, but can you see an overall structural flow there?
Yeah, I think we can design something.
Yeah. I mean, we said joking this morning, ChatGPT, tell me what the velocities are in 2D, but I'm just not going to do that. So please don't do that.
All right. I know there's a question in Virginia. So Ashish, has a question?
Yeah. Hi. Great.
Hello.
I was wondering if you see jumbos in other star forming regions, or do you see the frequency of jumbos vary in different parts of the region you are studying?
Yeah, so of course that was one of the first questions we asked. If is there something wrong with the JWST data? Are they just artifacts? No, they're not. Do we see them in other regions? Because other people like Kevin Luhman has been studying IC348, Mike Meyer, NGC 2024, Alex Schultz has been looking at NGC 1333. Similar regions, lower densities though. Typically, Orion is quite exceptional in that regard. And they are not finding objects below 2 Jupiter masses or so, and they're not finding much evidence for those binaries. But some of that's explained by the statistics. There's so many more objects in Orion, and if there's 20 pairs, maybe it's harder. But I know, again, it depends on them being real, right? Firstly.
The pairing is real.
The pairing is real. They are real pairs of physical objects, exactly what they are, whether they're in Orion or beyond. But you wouldn't expect to see them in Orion. Orion's way out of the plane, right? They're not going to be background objects.
Are there any special places in Orion? I mean, you had 5 altogether.
Yeah, so there are 25 or so in total, we think now, having ruled out half of them. They're not particularly distributed, apart from those 5, which are quite clumped. And maybe there's something special about what happened there, again, if they're in Orion. So we have looked in other regions. We are finding interesting things, let me say, without going too far, in other regions. But we haven't found a whole bunch of jumbos as such. But we are finding some other very JWST images which are archival, which we're looking through as well. So we are looking for them. And the other thing I wanted to say, we're looking at 2 other star-forming regions. We looked at the center of the Rosette Nebula, which has a much lower density overall, number density, but has lots of brown dwarfs, to see if we could find them there. We don't have a result for that yet. Those data are relatively new. And a galactic anti-center star-forming region called Sharpless 305, which we've looked at, and we have those data as well. That's quite far away, though, so we wouldn't expect to see very low mass objects.
We should have a look. We have some regions, but ours are generally further away.
Yeah.
But we have a Sharpless region. Okay, Ruben, we have time to come back to you, I think. I'm not seeing other hands, so if you have another question, Ruben, please ask.
Yeah, I have a ton, but for the sake of time, yes. Since you're showing this guy, the HH211 that is showing in every talk all the time, do you see absorption in helium-1 line or any hint in any of your jets or Tom's rays or Alessios?
No, because we don't have a bright helium background, and that's important. Even in Orion, the helium absorption features are very limited to what's known as the Huygens region. So the thing that Christian Huygens saw very early on, where the helium-1 is bright enough that we can actually see it as a background source. So when we move out into the larger area of the Orion Nebula, we don't see it anymore. Now, what we don't yet know is how you excite the helium-1 gas into that triplet state. That obviously involves energetics as well, so that it can sit there for a few hours before it decays or rather absorbs a background photon coming through. So no, we don't see it in HH211, HH212, or HH288.
That's because difficult to see. You don't...
Yeah, there's no bright helium-1 background. It's not to say that there is not helium in there, but it needs to be excited somehow too.
But in emission lines,
no, there's no helium-1 in any of the other flows that we've looked at.
And in Orion, there's no helium-1 in emission.
Sorry, does that mean, Mark, that we are in the same example of the fingers, that this feature of absorption helium only happens in Orion in a few places?
Well, no, that I wouldn't say, because there are plenty of regions with a lot of excitation and helium-1 from the background. We just haven't looked with JWST yet, because there's no ground-based filter that can look for this.
Yeah.
You need that filter with JWST. The other point to make there is, as I say, we don't know how the gas gets excited into that state. It may be different ways, depending on whether it's a circumstellar object, a diffuse cloud, a propelid, or a jet. There may not be one universal mechanism.
And let me just try and summarize. So the helium-1, it's atomic helium in an excited state.
Yeah.
The hydrogen,
metastable triplet state.
The hydrogen in that same gas is also an atomic hydrogen. Is a atomic hydrogen?
Well, remember, we don't. It's very hard to separate along the line of sight, I think. I mean, of course, there is lots of atomic hydrogen, ionized hydrogen along that line of sight, but we don't see features in hydrogen. But then it's not metastable, it doesn't have a metastable state either. So
okay, and its use might be for measuring mass.
Yeah, if you can make some assumption about how much helium there might be as a fraction of the amount of gas or the amount of dust.
Okay, we can take one last quick question from Lee. So please.
Yes. Hi, Mark. Since you just mentioned the HH212,
yes,
I was wondering whether you see any evidence for disk wind. There's some evidence from the ALMA.
I'm going to show you one picture of HH212. If I can find the right one. Hold on. So HH212 is this sort of supersymmetric jet that we discovered many years ago. This is the JWST image of it. You can see the high degree of symmetry about the protostar, which you can just see where the protostar must be in the middle there. And so if we zoom in, firstly, we can see over just 1 year, we see proper motions. And what we see here is, I wouldn't say we see a disk wind, because we're not seeing close enough down to the base of the flow. We're seeing reflection nebulae, which are changing over a 1 year timescale. So that's above and below the disk. But the reason I wanted to show you this, if you see that there's a point right in the middle of the picture, which is blinking there. Because it's blinking the way I've scaled the image, we know it's continuum and it's not moving. And you think, oh, is that the protostar at the very center? It turns out that it's not, and it's wrong in position by about 1/10 of an arc second compared to the ALMA data, because we have good enough astrometry that we know that the ALMA, where the ALMA stuff is. So we're not quite seeing down to the level where that disk wind stuff is seen in the ALMA data with JWST, because we can't penetrate into the center of the disk.
Very good. We could keep talking for hours and weeks and days, a long time about Orion, but we should stop now and thank Mark again for a great overview and
thank you.
Wonderful questions.